Let's do one more example of finding eigenvalues and eigenvectors. So let's find the eigenvalues for this polynomial, or for this matrix. So to find the eigenvalues, we can just take set the characteristic equation equal to 0. Just for variety, this time let's take the determinant of a minus lambda I. Remember, it doesn't matter whether you do lambda I minus a or a minus lambda I. It will change the polynomial, but the polynomial will have the same zeros. So either one is fine. So we're going to be taking the determinant of, let's see, 2 minus lambda, 1 minus 1, and 4 minus lambda. Okay, so we get 2 minus lambda times 4 minus lambda plus 1 for this determinant. When we multiply this out, we're going to get, let's see, 8 minus 6 lambda plus lambda squared plus 1. So we get lambda squared minus 6 lambda plus 9, and that's lambda minus 3 squared. Okay, so we only get one solution in this case. The only eigenvalue we get is 3. So let's find the eigenspace associated to this eigenvalue. So we'll just take our lambda equals 3 and put it in here. Write down a minus 3i. So that's going to be minus 1, 1. Minus 1, 1, minus 1, 1. And then when we row reduce this, you can see we're going to get 1, minus 1, 0, 0. And so the null space is the span of 1, 1. Okay. Now something funny has happened here, which is essentially we had two eigenvalues that happened to be the same, 3 and 3, right? I say two eigenvalues because 3 is a root of multiplicity 2 for this equation, right? Because of the squared there. So you might expect, since the multiplicity of this eigenvalue is 2, you might end up with two linearly independent eigenvectors to go along with it. But that's not the case here, right? We actually only got an eigenspace of dimension 1. So it's as if there's kind of a missing eigenvector, or a missing special direction for this matrix. Right? There is one special direction, a one-dimensional eigenspace, but there isn't another, even though it kind of seems like maybe there ought to be. There isn't. I should mention, it is possible for a matrix to have a single eigenvalue and a two-dimensional eigenspace. Just to show you one example of that, this is sort of a simple, silly example, but this matrix has a single eigenvalue, which is 3, and the eigenspace, ES for eigenspace, the eigenspace for this eigenvalue is actually, you can tell it's spanned by 1, 0, and 0, 1, because if you take either one of these vectors and multiply them by this matrix, what you get is 3 times the original. So this is actually all of R2. Right? So for this example, we have this repeated eigenvalue, and so it's multiplicity 2 as a solution to the characteristic equation, which is 3 minus lambda squared equals 0. Right? So this eigenvalue, for this example, the eigenvalue is a solution, a 0 of multiplicity 2 for this equation, and there actually are two different linearly independent directions in the eigenspace for this eigenvalue. So, sometimes it's one way and sometimes it's the other. So there's really no, if you have a repeated eigenvalue, there's really no telling how many dimensions your eigenspace will have without actually calculating it. So the eigenspace has to be at least dimension 1, because an eigenspace can't be just the 0 vector. And it turns out that the largest an eigenspace can be is equal to the multiplicity of the eigenvalue. But it really could be anywhere in between. So here we see with a multiplicity 2 eigenvalue, you might have an eigenspace of dimension 1 or of dimension 2. It just depends on the matrix that you started with.